So you are familiar with the Hawthorne experiment, and it's this unexpected results of this experiment, where even under poor lighting conditions, the productivity of the workers kept on increasing, has been known as the Hawthorne effect in literature. It's a very famous experiment. And actually, a more general term that is used is reactive effects. These are the reactive effects of the experimental setup. It of course tells us that the subject-object duality has failed completely in this experiment. The observers were influencing those who are observed. Now, we define and make clear three concepts that we use a lot in our profession. These are the concepts of efficacy, effectiveness, and efficiency. Now, the one with which we are most familiar is probably the last one. The efficiency concept is very well known to us. Effectiveness, as we said, is very important. Efficacy is maybe something new. So let's see what these all mean. Efficacy answers the question, does the means work? The means, there's the separation of ends and means. We want to reach an end, which is our objective. And in order to realize our objective, we use some means. Do these means work? It is the capacity to produce an effect. So efficacy is the capacity to produce an effect. For example, aspirin is efficacious against headache. If you have a headache and if you take aspirin, it works. It is efficacious against headache. But it's not efficacious against a broken bone. If you break a bone in your arm, aspirin will not help you. So efficacy is just this. Effectiveness answers the question, will long-term goals be attained? And we have discussed this. And efficiency answers the question, is resource use minimized? That is maintaining effectiveness with fewer resources used. So you see, efficiency and effectiveness are related. Efficiency is about maintaining or achieving effectiveness with fewer resources, at minimum cost, in other words, at minimum resource usage. Concern about efficiency should not conflict with effectiveness. We are now pretty clear about these, reading Aikoff's articles, etc., and I think you now realize this. For example, reducing inventories to save costs might run contrary to effectiveness because you might lose customers and sales revenue, etc. Whereas your long-term objective is to maximize your profits. If you try to maximize your profits by trying to minimize inventory costs, you may end up with an unexpected result. Okay, so they should not conflict with each other. Efficiency should complement effectiveness. So let's start, therefore, with the concepts of systems. Mostly I'm trying to follow the textbook here. Not exactly here, but generally. There are many classifications of systems. You are familiar with one classification. What was it? Open and closed systems. Actually, this is not a very powerful classification because we know that a closed system is probably not possible except the universe. If you assume that the universe is a single system, then I would ask you what is beyond the universe. So it is problematic, but that was one. Another classification is this one. This is quite useful. Natural systems. Natural systems, abstract systems, and social systems. This is nice. The natural systems, for example, the solar system, a frog, a girl, a boy. These are natural systems, an ecosystem. There are abstract systems like an algebra, the number system, etc. These systems can be closed, only the abstract system. If we consider them in their entirety as mathematics, for example. Then there are social systems, and we know that we can call them also human activity systems. And there are also the classification, not classification, but perceiving these systems in two ways, either as inside us or out there, independent of us, the epistemological and the ontological views. And we have argued that the first view, the epistemological view, will be more useful for us when we construct systems and systems models in industrial engineering. Now, let's consider some examples to see how we can view a system which looks like an ontology as an epistemological system. Let's consider, for example, an electric power supply system. An electric power supply system consists of several electricity generators which produce electricity by rotary motion of the alternators in a magnetic field, and that electricity is transmitted and then distributed to where they are needed at demand centers. Is this system an ontological system or an epistemological system? Now, you might regard that this system exists out there. We can see the transmission lines, you can see the power stations, etc. So it looks like as if it is part of reality. So an ontology. Ontology is about existence, as you should remember. So it exists outside of us. It includes generators, etc., transformer stations, etc. But does it also include rivers? Maybe you produce electricity from hydroelectric stations. And for example, this electricity that is produced has a price. You sell this electricity. So there's a pricing system. So the electric power supply system has these sort of extensions. If this is the situation, then a pricing system, is it something independent of us? Obviously, it is not. It is up to our decisions how to price electricity. So suddenly, the electric power system becomes, our perception of it as an ontological system is not very strong. It's not a very strong point of view because of these considerations. So it is best to regard all these systems as epistemological systems, because epistemology doesn't say that part of the system does not lie out there. It doesn't say that. It says it is better to have the system concept, as a construct, even though its parts may really exist. Okay? So that's the idea of the two types of what the system will include or exclude will depend on how we define the system, actually, on the purpose of inquiry. This can change from person to person. Also, it can change for the same person. Let's use the same example of the power system. Suppose the power system includes a river system where hydroelectricity is generated, and then engineer, for example, a power engineer who regards this power supply system taking water from the rivers and building dams, etc. He regards this system in one way when he is working, but suppose this same engineer is having a holiday and a vacation with his family in the river basin. The river is a nice place for having a picnic, for example. When he is doing that, he regards the same system from a different point of view, and maybe he will define the system differently in that case. So you see, the existence or the concept of a system depends primarily on the purpose of inquiry. Okay? Therefore, it is better to regard systems as epistemological constructs. It works much better in our practice of OR. Dellenbach, our textbook, provides definitions like this. You can read these, they are easy to understand. And you can also read The Nature of System by Russell Aikoff, the second reading we posted at the website. It does the same thing very usefully. I don't think we have to spend much time on this. You can just read these. The underlined components of the system are important. There are inputs and outputs. There's an environment. These are concepts we are familiar with anyway. So I think we can pass over this slide and make comments about some of these components. The most important component probably, or entity in systems, is the environment, the boundary. The boundary is the most important part of the system. Beyond the boundary, we have the environment. Now, we can identify for each system not a single environment, but a relevant environment. The relevant environment of the system provides inputs to the system, and there is a transformation process within the system. So these inputs are inputs to a transformation process, and receives outputs. The environment, the relevant environment, receives outputs from this transformation process. This is how we understand the system. It's an engineering definition of the concept of a system. Now, some of these inputs can be uncontrollable. We cannot control some of the inputs. Others are control inputs over which we have control. And for example, if we construct a mathematical model of such a system, these control inputs will be represented as our decision variables, as you know. So controllable, uncontrollable, and controlled inputs. We make a distinction between them. Another term for uncontrollable inputs is what? What do you think another term is? We call them parameters, system parameters. Parameters are given to us. We cannot change their values. For example, data in an optimization model, in a linear programming model, you minimize a vector Cx, the dot product of a cost vector with a decision vector Cx, subject to conditions Ax equal to B. A is the matrix, and B is the right-hand side, where X is greater than or equal to 0. This is the LP problem. What are the control inputs? Which variables represent the control inputs in this mathematical model? The X. What about the uncontrollable inputs? What are they? The data, A, B, and C. These are the data. We call them the data. Actually, these data are the uncontrollable inputs. They are the parameters. Okay. Now, the outputs include measures of performance. And in order to understand, in order to identify the environment, we have to set system boundaries. Okay, we'll stop here.